Hello everyone. Today we are going to derive the two-dimensional heat transfer governing differential equation. We call that as a two-dimensional problem because the temperature is going to be the function of both x-axis as well as y-axis. We have already derived the governing differential equation for a one-dimensional heat transfer system for a pin fin, in which case the temperature was a function of only one coordinate system, which means only one axis, that is one independent variable, that is x-axis. So we call this as a two-dimensional system because temperature can vary along the x-axis, and as you progress along the y direction, temperature can also vary along the y direction. Alright then, so let us first establish the physical scenario. What you see here is an engine. That's a symbolic representation that the engine is actually producing some heat, and you want to increase the longevity of the engine. So what you do is actually you provide a fin to dissipate the heat, and thereby you increase the lifetime of the engine. Otherwise the engine is getting choked sooner or later. So providing a fin is a nice way to increase the lifetime of the engine. That you can see that there is a rectangular fin that dissipates the heat. That's a symbolic representation. This can be a heat source that is produced by engine, but it can also be a heat source that is produced by a microprocessor, or maybe even it can be the heat source of from many different sources, right? So you want to dissipate the heat in order to increase the lifetime of the system. Okay, fine. So the way you derive the governing differential equation is you first consider a small calculus element. The one that you see green in color, that's the small calculus element that you see. I have considered the small calculus element. Maybe before you do that, what you have to do is you have to reckon a set of coordinates axis. This is going to be your x-axis, this is going to be your y-axis, and the small calculus element, this green square that you see, is considered at a distance of x from the left extreme end, and it is considered at a distance of y from the left extreme end of the coordinate system. So that's a small calculus element. So in the next page, what we are going to see is we are going to see the magnified view of this small calculus element. So this is going to be our dx, and this is going to be your dy. Mathematicians would not allow us to call this way because calculus means that you can actually evaluate the change in temperature with respect to x-axis or y-axis at a particular point. So the correct way to say this is del x and del y, but anyway, this helps us to do the mathematics in a very, very conducive fashion. So we can call this as dx dy, not a big mistake, but it's a convenient way to say that this is dx and this is dy. Fine. Okay, here we go. So you can see this is the highly amplified view of the small square that you consider in the fin, and you can see there is heat that is coming in towards the left hand side, and heat is going out on the right hand side. Okay. Similarly, if you look at this part, heat is coming in from the bottom towards the top, and heat is also leaving out in this direction, right? So heat is coming in along the x direction, and heat is going out along the y direction. And let us concentrate on the heat that is coming in along the x direction. The heat that is coming in along the x direction is proportional to the cross-sectional area. What is the cross-sectional area, by the way? It is the height, which is dy, and the depth, which is the thickness, right? So it's simply given as area, but the area, if you just expand it, it is dy, which is the height, and the thickness. The thickness is going along the z direction, so it's coming out of the screen, but it cannot be represented. So it's just a two-dimensional representation of your three-dimensional situation. So you have to exercise it in your imagination in order for you to understand this concept. So just try and think it through. So it's quite intuitive to say that the heat that is coming in from the left extreme end is directly proportional to the area, which is dy into thickness. And it is also directly proportional to the temperature gradient. Now, the way you think of temperature gradient is, you can think of a slope, right, which is given by the expression dy by dx. Maybe you consider the slope of your right angle triangle. So if you are placing a ball at the top corner of the right angle triangle, the ball is going to roll over because it comes from the higher potential energy is converted into kinetic energy, and the ball just rolls to reach the lower potential energy, right? So that's quite intuitive. So in exactly the same fashion, you can think of this as greater the temperature gradient, greater is going to be the heat transfer. Okay, so greater the difference between the temperature with respect to x-axis, in this particular case, greater is going to be the heat that is going to rush from the left extreme end towards the right. All right, so this is going to be the expression for heat that is coming in, and there is a proportionality constant, which is K, which is called as the thermal conductivity of the particular material. And you can see that the thermal conductivity of the particular material depends on the material. So it changes from one material to the other material. And you can see the quantity of heat that is going out, that is directly proportional to the cross-sectional area, and also the temperature gradient at the right extreme end. So it's basically the same equation, but except that you are just adding the suffix in, stands for the heat that is coming in, and out, the heat that is going out. In exactly the same fashion, you can just write the quantity of heat that is rushing in towards this calculus element from the bottom that you see here, and the quantity of heat that is going out. So it's essentially the same equation. That's one that is represented by the blue in color. We assume that the material is isotropic, otherwise you also have to add the suffix x and y for thermal conductivity. So in our case, we can assume that thermal conductivity along the x direction and the thermal conductivity along the y direction is going to be the same. So we assume isotropic property here. Okay then. And here you can see the quantity of heat that is lost due to convection. So when the heat is going from one medium to the other medium, in this case the heat is being dissipated from the solid medium, which is the fin, and the heat is getting dissipated to the atmosphere via the air medium there. So that is called as the convective heat transfer coefficient. So this fan is a symbolic representation. I'm not indicating that this forced convection is a must, but it's just a symbolic representation here. Okay, the convective heat transfer, the quantity of heat that is lost due to convection is directly proportional to the area, and it is also directly proportional to the temperature gradient. So this is the area dx dy. Because greater the surface area, greater is going to be the quantity of heat that is lost due to convection. And greater the temperature gradient, greater the quantity of heat that is lost due to convection. And the H is the proportionality constant. We call that as the convective heat transfer coefficient, that is H. So we assume that the convection is taking place on both the faces. So the other face is represented here. It's not going to be visible, but we assume that the convection is taking place on both the faces. All right. Next, this is indicating that there is some kind of heat that is generated from within the system. It's not possible for this particular scenario, but in some cases it's definitely possible. Say, for example, there is electric current that is passing through the system. Then in that case, heat is definitely generated. And also in the case of nuclear pellets, heat is generated because of the nuclear reaction. Some cases there can be chemical exothermic reactions, in which case the heat will be produced because of the chemical reaction taking place within the solid. So that is why this symbolic representation of the flames here indicates that there is some heat that is generated from within the system. And G dot is a generic term. It represents the quantity of heat that is produced per unit volume. And you want to find out the quantity of heat that is produced throughout the square, this calculus element. So you just multiply the volume of the calculus element by G dot. So it becomes G dot into dx into dy into thickness. So that indicates the quantity of heat that is generated. Now we know what is the quantity of heat that is coming in along the x direction, going out along the x direction. Quantity of heat that is coming in along the y direction and going out along the y direction. And quantity of heat that is lost due to convection, and we assume that the convection is taking place on both these sides. And also the quantity of heat that is generated. Okay, all right then. So all you have to do is you put all this together in order to get the governing differential equation. So the next slide that you can see, the quantity of heat that is coming in minus the quantity of heat that is going out, that's going to give you the quantity of heat that is stored. What comes in? Say for example, 10 comes in, 7 goes out, 3 is stored, right? So in exactly the same manner, quantity of heat that is coming in along the y direction minus the quantity of heat that is going out. So say 10 comes in, 7 goes out, 3 is stored. And also quantity of heat that is lost due to convection, that expression is there. And the quantity of heat that is generated, okay, because of some kind of reaction, or maybe there is an electric current that is passing. So there is a quantity of heat, maybe there is a nuclear reaction. The quantity of heat that is stored, that is given by the expression G dot dx dy thickness. So that gives the quantity of heat that is stored. So that is the mathematical equation. So in the next step, what I will be doing is this is dt, change in temperature, minus change in temperature. So what is change in temperature, dt? When it comes in, minus change in temperature when it goes out, that becomes d squared t, dou squared t, divided by dou x. See, I'm doing the mathematics very carefully here. It's dou squared t divided by dou x, not dou x square, right? So let us do the mathematics and exercise much precision and caution when we do the mathematics. It's dou squared t by dou x. And here also it's going to be k-a-y along the dou squared t by dou y. That's what I'm going to do in the next page. There you can see the quantity of heat that is coming in. It's going to be dou squared t by dou x into dy thickness plus dou squared t by dou y into this cross-sectional area, which is going to be dxt. The rest of the terms, the quantity of heat that is lost due to convection, and the quantity of heat that is generated, and the quantity of heat that is stored. Now what you do is, I'm going to divide the left side and the right side by volume. So if I divide the left side and the right side by volume, I'm not going to do any damage to the equation. So let me divide the left side and the right side by volume. So if I divide the left side and the right side by volume, what you do is dou x into dou x becomes dou x square. Dy thickness, they cancel each other out. Similarly, dou y into dou y becomes dou y squared in the denominator. Dxt and dxt cancel each other out in the numerator and the denominator. And similarly here, dx dy goes away, you will be left with the thickness. And similarly, the volume term completely disappears. And here you get the quantity of heat that is stored per unit volume. That's what you'll be getting here. Okay, let us look at the final differential equation that you are going to get, which is going to be kx into dou squared t by dou x squared plus ky into dou squared t by dou y squared minus 2h divided by thickness into t minus t infinity plus g dot is equal to the quantity of heat that is stored per unit volume. So that's the governing differential equation. I have told you that every governing differential equation holds a secret that is stashed inside them. All you have to do is you just solve the governing differential equation the right way. You're actually going to get the secret that enables you to take some very smart engineering decisions. In our case, the secret is the temperature. So if you solve the governing differential equation, you are actually going to get the value of the temperature. And once you get the value of the temperature at different points, that enables you to take the smart engineering decision, right? So before you just go ahead and derive the governing differential, go ahead and solve the governing differential equation. Of course, we are interested in the finite element formulation of the governing differential equation because sometimes the system can become very complicated, the geometry can become very complex, and the load and the stuff that is acting on the fin that can become very complex. So you have to come up with a finite element formulation in order to solve the problem completely. So in order to do the finite element formulation, we have Galerkin's weighted residual method. There you can see the expression for Galerkin's weighted residual method. It is integral of Wi into R into the domain that is equal to 0. Okay, so we are going to see Galerkin's weighted residual method and how to come up with the weak form of this differential equation. Once you have the weak form of the differential equation, that enables you to solve the governing differential equation. That enables you to come up with the finite element formulation. Once you have the finite element formulation, then you are pretty much there. You can solve any complex geometry, two-dimensional heat transfer by using finite element method. So in the next video, we are going to, in the part 2, we are going to see how to come up with the finite element formulation for the governing differential equation. And once you have the finite element formulation, what we will be doing is we will be deriving the convection matrix, we will be deriving the convection matrix, and we will be deriving the matrix that is analogous to force matrix due to heat generation, force matrix, sort of analogous to force matrix due to convection, and also the force matrix due to the heat flux. We will be deriving all these equations in the next part. So thank you all for your patience. Very much appreciated. Thank you so much.